Hello and welcome to today's video, 153, find minimum in rotated sorted array. So you're given an array of length n sorted in ascending order and it's rotated between 1 and n times. For example, you have the array nums of 0 to 1 and 7 and it can become 4, 5, 6, 7, 0, 1, 2 if it's rotated 4 times, 0, 1, 2, 4, 5, 6, 7 if it's rotated 7, etc., etc. So, given the rotated sorted array of nums of unique elements, we want to return the minimum element of this array, and we have to do it in O of log n time. Okay, let's take a look at the examples here. We have 3, 4, 5, 1, 2, and our output is 1 because the original array is rotated 3 times, so it becomes 1, 2, 3, 4, 5, and we have to return 1 because that's the minimum. Same thing with this one. It's rotated 4 times, and we want to return 0 because that's the minimum. It used to be 0, 1, 2, 3, 4, 5, 6, 7. And then finally for this one, we want to return 11 because it's rotated 4 times, it's completely reset again, and you want to return the the least value. Okay, so that makes sense. Let's go ahead and take a look at this example over here. So we have 3, 4, 5, 1, 2. So one thing that we could do in order to figure out where the minimum element of the array is think of conditions where like you take a number and you see whether or not it's sorted or not sorted. So, um, so what this question tells us is because you have to figure out that the algorithm is an O of log n time, and it's a sorted in ascending order array, it gives us a hint that we can use binary search. But if we just use binary search by itself, it won't work because having a pointer at the very left and a pointer at the very right won't be that useful because it's rotated, right? So we can think of different ways in order to change binary search so that it fulfills basically the criteria of this problem. So okay, let's say we have like a left pointer here, a right pointer here, and then we have like a regular pointer at the middle like this one. So how do we know that the middle number 5, basically whether or not it's like the stuff to the left and to the right of it is sorted? Well, if we look to the right here, we can see that 1 and 2, it's less than 5, and for all the ones on the left, it's all it's basically less than also, right? So a regular sorted array, everything to the right of it has to be greater, and everything less than it, like everything to the left of it has to be less than. So I guess we can kind of divide this into two different portions. So one portion is here, is where it starts, the right portion, and we have like the left portion over here, right? And we want to figure out how to get this number over here. So one thing that we could do is we can kind of figure out maybe a condition for how this right value, how to check whether or not this right value, like everything to the left of it is still sorted or not. What we could do is we can compare it with the value at the very left. So let's have a look at here. For number 5, we know that number 5 is greater than the element at the very left over here. This 3 value over here, because that's the middle pointer, right? For a scenario where it's within the, so we know for sure it's in the left portion that's sorted. So like the left portion that's been rotated up to here, we know it's sorted, we know everything is good because because like the middle value is greater than the left, right? Now, imagine we have like another value over here, like I don't know, like two again, or so, basically something like that. Um, well, it has to be an integer value, but okay, just imagine arbitrarily that the middle pointer is over here at 1. Well, if we compare the middle element at 1 and we compare the leftmost element of the array, we notice that it's less than the leftmost element, which doesn't make sense if it's sorted, right? So we can do a comparison here and check to see the middle to see, for the middle, we want to see check if nums at the middle is greater than or equal to nums at the left pointer. If it is, then what we can do is we know for sure that this element, like that this area is sorted already, right? because since it's greater, it doesn't it makes sense that it's is greater. So we can effectively rule all of this out. So we can rule all of it out and focus only on the left and the right pointer over here. So we can move this forward, make it equal to m plus 1. We'll make m to equal, the pointer to equal to m plus 1. And then if not, then we know for sure that, okay, let's say in a scenario where it's not over here, we set a medium over here, it turns out that it's actually greater, then we want to set the right over here to equal the medium minus 1. So we set the right pointer to search this area instead, because if the middle pointer is at the 1 and 2 value over here, then basically it doesn't make sense. We'll search for the 3, 4, 5 value over here. Now along with this, we should also do a comparison, while this is happening. Let's do r equals m minus 1. While happening, we want to do comparison. Maybe we can have a result variable. So result equals I don't know, some arbitrary number. Let's say the first value over here. And with this first value, what we can do is we can check to see whether or not it's the minimum, right? So we can do res equals, we can find the result and make that the minimum of itself and then the current middle value. So nums at medium. So this way, if we go about what we were talking about before, where you have the left and the right pointer over here, and arbitrarily the middle pointer is at 1, it'll check to see what the minimum is. So it'll have that set as the, basically, it'll be set to 3 originally, and it'll turn it to 1, and then it'll check this portion over here to check for another smaller value before moving on, so on and so forth. As we know, there isn't any smaller value than 1 over here. So at the very end, what'll happen is it'll return the 1 result, which is what we want. But let's say in the scenario we were talking about before, where we have the left and right value over here, we check to see what the medium is. We check to see, is it greater? It is. So if this is sorted, that means we're already on the left portion. That's already been sorted. So we don't need to search this anymore. We go ahead, move the left pointer over here, and then what we do is we grab the leftmost value again. Basically, we grab the leftmost value, and then we check to see whether or not we check to see whether or not that's less than the current value of the result, and then we can return that at the very end. So yeah, and this happens if the left pointer, the number at the left pointer, right, is less than the number at the right pointer. Otherwise, you don't have to perform that check. Yeah, so if we go ahead and implement this now, what we can do is we can set the result to equal arbitrary value nums at the very first elements, and then while the left is less than or equal to the right, what we can do is first check to see whether or not the nums at the left is less than nums at the right. So for this example, let's say we have left and right over here. I check the medium. Is the left less than or equal to the right? Well, no, it's not, so it'll skip this. But if it is, that means it's within the sorted portion, right? So then we want to set the result equal the minimum of the current one and nums of at the left pointer, because that's the very beginning of that portion of the array. After that, what we're going to want to do is check and do the binary search. So a regular binary search, left plus right, divided by 2, because medium equals this, because basically adding those two together and finding the middle portion of it. We then check to see the result and check to see whether or not it's the minimum of the result and the current middle pointer. So in this situation, it's 5. And then what we can do is we can look at our portion, or look at a condition that we were talking about earlier, check to see whether or not if nums at the mid pointer is greater or equal to nums at the left pointer. And then after that, we can then move the left equal to medium plus 1 equals m plus 1, And then otherwise, we go ahead and do set the right equal m minus 1. And at the very end, what we can do is return that final result. And this would be a O log n time complexity because you're cutting down the amount that you have to search in half at every single time over here. So let's go ahead. Oh, forgot a colon over here. Let's go ahead and take a look at this code one more time. We set it to some arbitrary value. While the left is less than or equal to the right, we check to see whether or not the sorted, right? The element at the very left pointer is less than the element at the right pointer. If it is, then we're going to want to set the result to equal the minimum. Oh, actually, then we're going to want to break this because, yeah, we want to break this and then return that final result afterward. Otherwise, we want to continue to do the binary search. Basically, check to see whether or not the current middle value is at the minimum. Check to see whether or not the condition is valid. If the middle pointer, right, if 5, let's say here, is greater than the left one, then we want to rule out all the ones to the left. Likewise, for the right one, we want to rule out all the ones on the right and continue the search for the medium, basically medium points at every single time. So if we go ahead and run this, oh, right, we forgot to define the left and right pointer. So we'll do left and right, and we'll set that to 0 and length of nums minus 1. Go ahead and run that again. Okay, there we go.